Let us discuss chemical equilibrium. Now we'll see what is equilibrium. We'll see what is called equilibrium. Now we will take a vessel. In the vessel we are taking water. Up to this level water liquid we are taking. For example 100 ml. 100 ml of water we have taken. To this let us add sugar. Let us add sugar and stir it well. The sugar dissolves in water. Sugar dissolves in water completely. Again add some more amount of solid sugar. Let it dissolve. Like this go on add solid sugar till it can dissolve, till it is having a capacity to dissolve solid sugar. Okay, at last we have added a trace of sugar and we made it to dissolve. Now we got what in the sense sugar solution. We got sugar solution. We got how much sugar, solid sugar you added, that much have dissolved completely. Okay, that much have dissolved completely. Now let us add 1 gram of sugar. 1 gram of sugar we are adding. We are stirring well, stirring the contents well. Then we are seeing the resultant. How the resultant is there we are seeing. How the resultant is there we will see. Here what is there means in this place sugar crystals present. Sugar crystals present. How much sugar crystals present means 1 gram present. Here what is there means sugar solution is present. Here sugar solution is present. Sugar solution is present. Now see, here we prepared sugar solution. To this we added 1 gram of solid sugar. We stirred the contents very well. We stirred the contents very well. Then we left for some time. We got here at the bottom we got sugar crystals. How much in the sense 1 gram. Above sugar solution is there. That means this indicates that this solution is unable to dissolve any more amount of sugar. That means this solution is unable to dissolve any more amount of sugar, which indicates it has dissolved sufficient sugar molecules. It is having sufficient dissolved sugar. It is unable to dissolve any more amount of sugar. Okay, such a type of situation is called a saturated condition. Therefore this is called a saturated solution, we can say. This solution we can call it as saturated solution because it has a dissolved sufficient amount of sugar. It is unable to dissolve anymore. Okay, to this saturated solution let us add 1 gram of radioactive sugar. 1 gram of radioactive sugar we will add it. Stir the contents very well and leave the system for sufficient time. We are leaving the system for sufficient time. What is the resultant we are getting, that we will see. So we left the system for sufficient time. Here what is there in the sense at the bottom sugar, solid sugar is there. Sugar crystals present. Sugar crystals present. How much in the sense 1 gram. Here what is there means sugar solution is there. Here sugar solution is present. Let us filter this. Let us filter this. On filtering, what we will get in the sense sugar solution separate, sugar solution separate, and sugar crystal separate. Sugar crystal separate. How much sugar crystals in the sense 1 gram. 1 gram of sugar crystals we added. That 1 gram we got it back. Sorry. Now we will take a counter called Geiger-Müller counter. This Geiger-Müller counter will identify radioactive rays. Radioactive rays. Radioactive rays means alpha rays, beta rays, gamma rays, like this, etc. Which will emit radioactive rays? Radioactive substance will emit radioactive rays. Radioactive element, radioactive substance will emit radioactive rays. These rays will be identified by this counter. Many counters are there. Scintillation counter is there. Many counters can identify radioactive rays. Radioactive rays emitted by radioactive substance. Okay. Now, we are taking this sugar solution to Geiger-Müller counter. Geiger-Müller counter says that it is emitting radioactive rays. This sugar solution is emitting radioactive rays. This sugar solution emit radioactive rays. It is emitting radioactive rays means this sugar solution contains radioactive substance. Okay. This sugar crystals we will take for Geiger-Müller counter. It is emitting radioactive rays. It is emitting radioactive rays. This 1 gram of radioactive sugar we are taking to Geiger-Müller counter. It emits radioactive rays. It says that it is emitting radioactive rays. But these are not emitting radioactive rays. These are not emitting radioactive rays. Therefore, in this radioactive substance is not present. In these radioactive substance not present because these are not emitting radioactive rays. That is said by Geiger-Müller counter. It is emitting radioactive rays because it is containing radioactive sugar. It is containing radioactive sugar. Therefore, it is emitting radioactive rays. This sugar solution is emitting radioactive rays. That means in this dissolved radioactive sugar is present. That indicates that in this dissolved radioactive sugar is present. Dissolved radioactive sugar is present. The sugar solution is emitting radioactive rays. That indicates it is containing dissolved radioactive sugar. This sugar crystals emitting radioactive rays. Why? Because this radioactive sugar we added. That's why. Okay. Now, here this radioactive sugar is emitting radioactive rays. This how much radioactive rays it is emitting means X curie. X curie. Curie is the unit. This 1 gram of radioactive sugar emitting radioactive rays. How much radioactive rays it is emitting means X curie. Curie is the unit. X curie it is emitting. This sugar crystals emitting radioactive rays. How much in the sense X minus Y curie. X minus Y curie. This sugar solution is emitting radioactive rays. How much in the sense Y curie. Y curie. So now you got an idea that how much radioactive rays it is emitting. How much radioactive rays it is emitting means X curie. This sugar solution is emitting Y curie. This sugar crystal is emitting X minus Y curie. What this radioactive sugar we have added to which solution? Saturated solution only, no? To the saturated solution we have added radioactive sugar. Saturated solution means what? It has got sufficient amount of dissolved sugar. It cannot dissolve any more amount of sugar crystals. Since it is saturated, it is unable to dissolve any more amount of sugar crystals. It is unable to take any more amount of sugar to dissolve. It is unable to allow. It is unable to allow sugar crystals to dissolve. That is the meaning of saturated solution. We got an idea, no? Now, to this saturated solution, we added 1 gram of radioactive sugar. Now, this sugar solution here, this is stirred well and left it for sufficient time. What had happened means here sugar crystals deposited down. How much in the sense 1 gram deposited above sugar solution is there. This sugar solution is having radioactive sugar. In this sugar solution, dissolved radioactive sugar is there. That is confirmed from this experiment. In this sugar solution, dissolved radioactive sugar is there. That means this added radioactive sugar has gone for dissolution or not? If it is not going for dissolution, how the sugar solution will show radioactivity? How the sugar solution will emit radioactive rays? So this sugar solution, though this solution is saturated, this solution is saturated only. Even then, this sugar crystals dissolved. Sugar crystals has gone for dissolution. That means in this saturated solution, sugar crystals is converting into dissolved sugar. Dissolution is possible, though it is saturated solution. Saturated solution in the sense it is unable to take any more amount of substance to dissolve. Even then, though it is saturated solution, sugar crystals undergo dissolution. That means a solid sugar is converting into dissolved sugar. That means a dissolution is possible even in saturated solution. Sir, in this saturated solution, dissolution is possible, we said. Okay, dissolution is possible. It is saturated solution, even then dissolution is possible. Sugar crystals converting into dissolved sugar. But this on filtration, we are getting back 1 gram of sugar crystals. That means concentration of sugar in this solution, concentration of sugar in this solution remains same. How much in this saturated solution, how much sugar crystals we added, that much sugar crystals present at the bottom. Here 1 gram of sugar crystals we added, that 1 gram of sugar crystals present at bottom. That means how much amount of sugar crystals converting into dissolved sugar, that much amount of dissolved sugar precipitating. Okay, how much amount of sugar crystals going for dissolution, equivalent amount of dissolved sugar precipitating, equivalent amount of dissolved sugar precipitating. Okay, that means in the saturated solution, two things are taking place. One is called dissolution, another one is called precipitation. Dissolution is possible, precipitation is possible. Dissolution in the sense sugar crystals dissolving, going into dissolved sugar, going into become dissolved sugar, while equivalent amount of dissolved sugar from the solution is precipitating. Therefore, we can say rate of dissolution and rate of precipitation are equal in the saturated solution. In the saturated solution, rate of dissolution and rate of precipitation are equal. That means the saturated solution is in what with the sugar crystals. The saturated solution is in what with the sugar crystals, in the sense is in equilibrium with the sugar crystals. This equilibrium is called physical equilibrium, we can say. This is called what we can say? Physical equilibrium. Okay, so that means this equilibrium is a static equilibrium or a dynamic equilibrium. Which one shall we say? This equilibrium, shall we call it as a static equilibrium or a dynamic equilibrium? Which one, in the sense this equilibrium we can call it as a dynamic equilibrium. Why? Because dissolution takes place continuously while precipitation takes place continuously without stop. Continuously it will take place. It will not go for stop at all. It will not stop at all till we are precipitating, till we are filtering. Even after filtration, now it is saturated solution. In this saturated solution also, precipitation and dissolution both are taking place. How? We have filtered completely? No. That means a trace amount of precipitate will be there that we are unable to see. Therefore, a saturated solution, in the sense in the saturated solution, physical equilibrium will be there between what in the sense between dissolution and precipitation. So in this solution, rate of dissolution is equal to rate of precipitation. That means this solution is attained what in the sense equilibrium, we can say. This solution has attained equilibrium. So equilibrium is possible at when? Okay, in this case, for this solution, this is equilibrium. So and so time equilibrium is attained, we got an idea. Generally, equilibrium means what? When equilibrium is possible, is it differ from one place to another place or what? That we will see. Okay, generally, general definition for equilibrium in the sense rate of forward reaction is equal to rate of backward reaction. Like this we can say. So now we will take another example for this equilibrium. We will take, now we will take a vessel. We will take, in this vessel, let us take liquid water. Liquid water, pure liquid water will take. Pure liquid water will take, and we will close this vessel. We close this vessel. Here what will be there? In the sense air will be there. Let us remove this air completely using vacuum pump, and we will make this place as vacuum. We made this place as vacuum. Now let us connect this to manometer. Manometer says reading 0. Why manometer says reading 0? In the sense here there is no the vapor molecules, there is no gaseous molecules. That's why manometer says 0 reading. As time passes, what happens means manometer shows pressure. Manometer is showing pressure means here some vapor molecules will be there or gaseous molecules will be there. We made it vacuum, we closed. Therefore, atmospheric air can't enter here. Atmospheric air can't enter here. Therefore, atmospheric air is not present, but manometer shows pressure in the sense here some vapor is there. What vapor possibility is there? Only possibility water vapor possibility. That means this water liquid is going for evaporation. Liquid water is going for evaporation and becoming what in the sense water vapor and becoming water vapor. Therefore, the manometer shows pressure. As time passes, what happens means as time passes, manometer shows increase in pressure. Increase in pressure. That means amount of water vapor increases. Amount of water vapor, what happens means goes on increasing. So, at at a certain time, at a certain time, at a certain time, the pressure exerted by the water vapor attains constant value. Then onwards, what happens means then onwards, as time passes, the pressure exerted by water vapor remains constant. There is no change. As time passes, after attaining certain time, the pressure remains constant though time rises, though time passes. What is the reason? Here, what is happening? Liquid water is going on evaporating. A liquid water evaporates. At a certain time onwards, the pressure exerted by water vapor remains constant. That means, what about amount of water vapor here? At this time onwards, amount of water vapor, how it will be there? Amount of water vapor, how it will be there? Do you say it remains constant? Do you say, or it increases? Do you say, or decreases? Do you say? In the beginning, what had happened? Pressure exerted by water vapor increased. We said amount of water vapor increases. We said after attaining certain time, the pressure exerted by water vapor remains constant though time passes. That means amount of water vapor remains constant. Is it meaning? Yes. Amount of water vapor remains constant. Amount of water vapor remains constant means, shall we say that evaporation stopped? Shall we say evaporation stopped? Because why we are saying evaporation stopped? In the sense amount of water vapor remains constant, therefore evaporation stopped, shall we say? Sir, what experimental analysis says? Whether evaporation stopped or not. The experimental analysis says that evaporation has not stopped, it is continued. It continues. It continues. Experiment says that evaporation has not stopped, it continues. Evaporation is not stopping, it is continuing, but amount of water vapor remains constant means on evaporation, water vapor is producing. What happened to that water vapor? Where it has gone? It is closed. It is closed in the sense it can't escape. Water vapor can't escape to outside. But manometer shows constant value. Manometer shows pressure constant. As per manometer, amount of water vapor should remain constant. But experiment says that evaporation continues, not stopping. Evaporation is continuing, but amount of water vapor remains constant. Evidence is manometer shows pressure remains constant. That means on evaporation, producing water vapor, what happened to that? Produced water vapor, where it has gone? For that only possibility, that has to condense and should become liquid water. That is only possibility. There is no other way. So the produced water vapor is condensing back to liquid water. How much water vapor should condense and to convert into liquid water? At this time onwards, how much water vapor is producing due to evaporation, that much water vapor should condense back into liquid water. Then only amount of water vapor here remains constant. Then manometer will show constant pressure. Okay. So here what happens means at this time onwards, that means pressure remains constant. At this time onwards, amount of water vapor remains constant, we are saying. Though amount of water vapor remains constant, evaporation continues. Due to this evaporation, how much water vapor is produced? Equivalent amount of water vapor here condense back to liquid water. Then only in this place amount of water vapor remains constant though evaporation continues. Then we can say pressure remains constant. Okay, that means this process is called what? In the sense condensation. So in this one, what process and all taking place means one is evaporation, another one is condensation. Evaporation means what? Liquid water is converting into water vapor. Evaporation and condensation both are taking place here. Okay, so in that place evaporation is taking place, then condensation is taking place. How the rate of these two will be there? Such that amount of water vapor in this place remains constant, for which is said by manometer. Manometer shows constant pressure. Means amount of water vapor here remains constant. That means how the rate of evaporation and rate of condensation will be there at this situation. Do you feel that rate of evaporation and rate of condensation will be equal? Yes. Rate of evaporation is equal to rate of condensation. This stage is called a equilibrium stage. That means system has attained equilibrium. We can say. That means water vapor is in equilibrium with the liquid water. Water vapor is in equilibrium with the liquid water, we can say. So when water vapor is in equilibrium with the liquid water, that time this water vapor is exerting how much pressure? That pressure is called vapor pressure of water, otherwise aqueous tension. Otherwise we can call aqueous tension, we can call. Okay. So what is vapor pressure of water? What is aqueous tension? The water vapor, when it is in equilibrium with the liquid water, exerting how much pressure, that is called vapor pressure. So vapor pressure, if you want, means first condition is what? Water vapor should be in equilibrium with the liquid water. Then this water vapor exerts how much pressure, we have to see. This water vapor exerting how much pressure, that is called a vapor pressure of water. Another name is what? Aqueous tension. Okay, this water vapor exerting how much pressure, that is called a vapor pressure of water, we can say. Another name is what we can say? Aqueous tension, we can say. Okay, sir. So what is vapor pressure of water? What is called aqueous tension? That we got an idea. Sir, this is called physical equilibrium. This equilibrium is called physical equilibrium because here equilibrium possible between liquid water and water vapor. That's why we are calling this as a physical equilibrium, we can say. Sir, now we will take a camphor. We will take camphor. We are taking it is solid. Camphor is there means by smell we will identify a camphor is there. We will identify camphor. Suppose we are keeping camphor in the sense we will get that smell. That means we are getting that smell in the sense camphor is converting into vapor form. Camphor is converting into vapor form. That vapor enters into our nose, so that we are feeling that camphor vapor smell. We will get it. Then we will say camphor is present. Suppose this camphor is packed in the plastic cover tightly, properly packed. Suppose this camphor solid is packed closely in the plastic cover. Then what will happen? It will convert into camphor vapor or not? This solid camphor is converting into camphor vapor or not? Of course it is converting. Then what will happen? This camphor solid is going on converting into camphor gas, camphor vapor. This camphor solid is going on converting into camphor vapor. After certain time, what will happen? Here equilibrium will be attained or not? Between camphor solid and camphor gas, equilibrium is possible or not? So this equilibrium also called what? Physical equilibrium. Between solid and vapor, equilibrium is possible. So which and all equilibrium, and we will see. Now we will take one example, melting. Melting in the sense water, solid water into liquid water also coming for equilibrium. This is melting. Solid water is converting into liquid water. This melting is possible at this melting will attain equilibrium at where? Okay, it will be at equilibrium position at its melting point. At its melting point, this system will be in equilibrium. Between solid water and liquid water, equilibrium will be there. At which temperature? In the sense, at its melting point. At its melting point, equilibrium is possible. Similarly, liquid water is in equilibrium with the water vapor. At which temperature? In the sense, at its boiling point. At its boiling point, liquid water and water vapor will be in equilibrium. Will be in equilibrium, we will say. Okay, these are called what? In the sense, physical equilibrium, we can say. Similarly, what is possible? Chemical equilibrium also possible. Set. So what is chemical equilibrium? What is the example for that? That will take. For example, we are taking Haber's process. Haber's process will take. In the Haber's process, we are taking nitrogen gas and hydrogen gas. These are reactants. We are taking initially reactants. These reactants undergoing reaction, undergoing chemical reaction and give product. Okay. Now